everyone, this is Dr. Speranza, and today we're going to be working on my stats workshop. And for this workshop, we're going to learn probability. Anything that has to do with probability will be in this workshop. So if you don't know probability, do stick around and watch with my students today at Marshall Community College. Okay, so this is how dependent becomes independent. So let's have another example of this particular rule in probability. Standard deck of cards. Now, answering probability on a standard deck of cards is going to be tricky if you don't know your standard deck of cards. Let's keep it simple. What's the probability of getting a face card? What we know is that the denominator is not going to change. It's 52. We just need to figure out the number of success. Face cards, there are 4 suits, right? How many face cards?
3.
King, queen, jack. 12 out of 52. All right?
Oh, yeah.
Okay, let's have another one. What's the probability that when you pick a card, the card that you will pick is a number less than...
Just ace cap.
So what is the probability that when you pick a card, it's going to be a number card, but it needs to be less than 5?
16.
Numbers less than 5 are
2,
2,
3,
3,
and 4.
and 4.
Yes.
There are 3 numbers that's less than 5. And how many suits?
4.
What's 3 times 4?
12.
That is why probability can be extremely simple or frustratingly confusing.
I'm not confused.
That's why it's extremely important that you know your sample space really well, and you need to be able to visualize it, because probability is easy when you're visualizing the sample space. And that's basically the importance of our lesson or workshop today. Understanding that you really just need to know your sample space, and whatever question that is given to you involving probability is going to be a lot easier and less frustrating. Right? So keep that in mind, because you're going to be seeing a lot of sample spaces again. Okay, answer this. Drawing 2 kings from a deck of cards. Alright, deck of cards. I pick a card, it's a king. I pick another card, it's another king.
Did you put the first king back? No.
Did I return it?
No.
Alright. Let's have another scenario that is the same as this probability. Standard deck of cards. 1, 2, 2 cards. They're kings. Alright, give me the probability of that happening. Let's begin. Alright, so is this a dependent event or independent event? Dependent, because the first card you pick is dependent. The second card that you're going to pick is dependent on the first card that you picked, right? So this one is a dependent event, which means the sample space is going to change, because the probability of getting the first king is what? 4 out of 52. But what about the probability of getting the second king? Is it also going to be 4 out of 52?
No.
No, because assuming that you pick the card that is a king, there are only 51 cards left and 3 kings, right? Theoretically. That's why sometimes it's called theoretical probability, because we just need to be mindful of the theories to be able to answer this problem. And then, is this an AND or an OR operation? AND, because they need to be exactly king, right?
One king and another king.
Oh, I said 1 king and another king, right? Yes, that's right. So, you're going to multiply. So, you're going to multiply for this particular probability to happen. So 4 out of 52 times 3 out of 51 is going to be a big number in fraction form, but in decimal form, it's going to be 0.0045, which is how much in percent form?
0.45%.
It's not even 1%. So the probability that you will get 2 kings when you pick a card, when you pick 2 kings from the standard deck of cards is really, really small. Alright, so this is how we compute for this particular dependent event on drawing a standard deck of cards. 0.45% is the probability of getting 2 kings. So if I come up with different problems involving standard deck of cards, you should know how to formulate it. Another example would be, what's the probability that when you pick 3 cards, okay. What's the probability when you pick 3 cards, it's going to be a number card, a face card, and an ace? Ooh, this is exciting. Probability that it will be a face, a number,
How many numbers are there?
and an ace.
Oh,
Two, nine, right?
3, 4, 5, 6, 7, 8, 9, 10. There's 9.
Just give me your answer in fraction form and give me your answer in decimal form so we can visualize the percentage of this particular event happening. Okay, give me the first fraction. Getting a face is,
Horrible. Because when you asked us, you said number
but
face.
it doesn't really matter because the
It does.
denominator is,
Yeah.
yeah, right? What about the number cards?
36 out of 52.
52.
Oh, so you're
Oh, I
going-
did it.
Yeah.
Okay.
I did that one first.
As long as it's changing.
Yeah.
What about ace?
It's 4 out of 50.
Yeah.
Now, does it matter if the denominators are changing on each of the events?
No.
No, because multiplication is multiplying the top and multiplying the bottom, and it's commutative, so
Yeah.
your answer will still be the same. Alright, what's the fraction form?
1728
1728,
divided by 1326.
132,
2600.
132,600?
Yes.
Oh my god. And what is it in decimal?
013.
0.013?
Yeah.
So about,
1.2.
oh. So the probability of this happening is more likely than getting 2 kings in a standard deck of cards. What do you mean, wow?
I'm just amazed.
We just computed it, right? What is so amazing about it? We already know that. So that is why you need to know your sample space, because probability and statistics is really fun if you know your rules and you can visualize the sample space. And the more you visualize your sample space, the easier it gets. Got it? And also make sure that you're understanding the question, because if you don't, like,
Yes.
am I replacing the card? Is it one at a time or is it 3 and 1 go? It doesn't matter, right? Okay, now another form of probability that you need to learn in AP statistics is answering probability in table form. Because probability is not just theoretical or classical probability, which involves flipping a coin, drawing a card. Sometimes it's on real situation. Most of the time it is used in survey form. Alright? So this is an example of a survey. So they asked this many women and asked about their status, marital status. And they come up with a table like so. So let's say they asked 250 women and they asked if she's never married, married, widowed, and divorced. And they count the number of women who answered this, and that, and then divided it by the total. Got it? And now they have a probability model. This is called a probability, if I can spell, probability model.
Sorry about the too, so.
Huh?
It's right there. It says here's the probability model.
Ah.
So you can just look at that.
And another term that we use for this probability model is one-way table. Because it's just one way. And to be able to verify if a probability model is a legit probability model, which is a question in AP Stats, how are you going to verify if it's a legitimate probability model?
You add it together, and if it equals 1 or 100%.
Alright. So if it's equal to 1 or approximately equal to 1, then it is a legitimate probability model. Now that we know, is this a legit probability model?
Probably.
Let's just say yes because we don't have time anymore. But yes, this is a legitimate probability model. And let's answer a probability question like this. What's the probability that when you select a woman from this particular probability model, it's a woman that's not married? What's the probability that in this group of women, that particular woman that you pick or choose is a woman that is not married. Okay, not married. Is not married the same as never married?
No.
No, of course not.
Not married.
This is the challenge in statistics or probability question. When you try to reason out or justify a thought that you think is right, when you are just specifically just being asked to answer this particular question, right? Okay, there are two ways on how to answer this problem. One way is what we call as the complement of an event. Do you know what complement is?
It's the not.
It's the not. It is the missing part of a whole, right? So in this case, the operative word is married. And we have married, which is happen to be not married, right?
So it's just one.
That's one way of answering this particular problem. This is one way of answering it. What is another way of answering it? Adding them all up. 0.298 plus 0.005 plus 0.075. So, again, this is how you are formulating your event in your head and how you're going to execute your answer. Both of them will give you the same result, right? Which is what? Point what?
378.
And it is 0.378.
Wait.
Alright, same probability model, but this time I want you to compute for a person that's never married or divorced. What's the probability that we're going to be selecting that particular person in this question?
How do you write it with like the notation?
With the notation,
Like the U and N.
That's what
Those
This
I get
thing
confused on that.
and then this
Oh,
thing.
or the intersection and the union,
For when you do the.
or is
Yeah.
or is union, letter U, intersection is and. Right, what's the answer?
0.37.
So basically, you're going to be working on the probability of never married, which is this one, and add it to the probability of a woman that is divorced, and then you add them up, and that is the answer to your probability question. Boom, boom, boom. So therefore, there are 37.3% of women in the group that are either never married or divorced. Got it? Okay, recap. So far, we did classical or theoretical probability. We did one-way table. We did independent and dependent events. Now, we're working on two-way tables. All right?
Since we're gonna let- I have a pencil.
Now, how do you construct a two-way table? A two-way table needs to have two variables. For example, let's create a two-way table right now. There are only 6 of you.
Numbers and bands.
Lace, not lace.
What?
Shoelaces.
She's the only one. She's still the only one.
I'm special.
And let's say...
I'm the only one. Oh man.
So, this is an example of a two-way table because we have two variables. Type of cell phones and type of shoes you're wearing, right? Alright, let's start with lace and iPhone. Who is wearing shoes with lace and has an iPhone? Four plus one, 3 plus 2.
Okay.
Legitimate.
Oh,
Alright. So, why is this important that you know how to work on probability questions involving two-way table?
because I'm giving
Like this. What's the probability that if I select student in this group, it will be a student with an iPhone?
3 out of 5.
iPhone is 3 out of 5. And that is correct. What about the probability of a student iPhone or laced shoes? How are we going to compute for a student who happens to have an iPhone or shoes with shoelaces? So it's addition, right?
Yes.
So all you need to do is to add all the person who happens to have an iPhone and laced shoes. What are the what are those people?
3 and 4.
iPhone,
2 and
iPhone, right?
Yeah.
Lace.
4.
So what's that?
5.
5 out of?
5.
Is that true that all of you have laces and
4 shoes.
iPhone?
Negative. Or.
Oh, but one of them is wearing. No. 1 plus 2 plus 2. Right.
Oh,
Because it's an or.
Okay,
It's
okay.
either someone with an iPhone or shoelaces. Is
I-
that correct?
I-
If I choose someone here, one of you will have either lace. Yeah.
Oh, okay. Never mind. I was adding
Either.
that one twice.
And this is why you need to know your language in probability and statistics. Because what's the difference if my question is probability of iPhone and lace shoes?
Both conditions.
Both. So it will be lace and iPhone, right? And the intersection is 2. So if it's an AND operation, it's an intersection. Now you're understanding the symbol is connected to the formula. So it's 2 out of
5.
which makes sense. The AND operation is always smaller probability than an OR operation, right? Because the OR operation 100%, AND operation it's going to be 2 out of 5. Union, intersection. All right. So now that you're learning too much from me, let's give a better two-way table. So this one is a two-way table. So they took a survey in a certain university and they asked around if the students have ear piercing or no ear piercing or no ear piercing, either male or female, right?
Yes.
Right?
Yes.
Because male can wear earrings, right?
Yes.
All right.
Why
'Cause
don't you have any?
I used to. All right. So let's compute for this probability. And this is Dr. Sobrana. Thanks so much for watching this video. And if you haven't liked this video, please like, share, and subscribe to my channel. Bye!
Mapasan. Yung balat. Ng lechon. Bakbakwa. Balbakwa.
Chicken.
Chicken lechon.